Okay, good morning. Welcome back to the natural language processing class. So for this week, we continue structured prediction. So this will be the last topic in structured prediction. So we look at a quite different paradigm in predicting structures, which is called transition-based methods. So today's lecture is going to consist of 4 parts. So first of all, we take a look at what is transition-based methods. And then we look at 2 problems, constituent parsing and dependency parsing, for illustrating how you build a transition-based model. As the final topic, we discuss joint models, which is effective for using transition-based method, which can also illustrate the advantage of this paradigm. Okay, so first of all, let's look at what is transition-based methods. As you may recall, all the method we discussed so far takes an input, right? And then tries to build an output structure on top of the input. What we did is we parameterized a model to score different structures. And then for training, we try to calibrate the score so that a higher score reflects a more correct structure, right? So if you think about hidden Markov model or conditional random field for label sequences, right? They score a sequence of labels for distinguishing good sequences from bad sequences. And similar things apply to semi-CRF and tree CRFs, right? So we directly calculate the probabilities of structures given the input. And we call this kind of paradigm a graph-based paradigm, where graph denotes the structure, right? So our modeling target is how good the output structure looks like. So for transition-based models, right, the paradigm is different in the sense that rather than modeling the output structure directly, we model the construction process of the output. We treat the output building process as a state transition process, where the state refers to a state in a finite state automata or finite state transducer. Okay. The actions which transist state from one to another are incremental output building actions. If you think about sequence labeling, it might be an action to add a label on a particular input incrementally. Okay. So we transform the output construction process into a finite state transition process, okay, where states corresponds to partly built outputs and actions correspond to incremental output building steps, okay. The modeling target is the state transition process rather than the output structures directly. Because of this, we call our paradigm transition-based paradigm in contrast to graph-based paradigm in the previous few lectures. So let's take an animation, right? So what is a transition system? We start from a start state, okay, which corresponds to an empty output. And then we incrementally apply action after another. For example, if I apply A1, we translate the start state to S1, the first state. which I incrementally built the output by a bit. And then I continuously apply action after action, A2, A3, until AI, until AN, for example. And we reach a final terminal state. And in this terminal state, we have the full output. Okay. So the whole action sequence corresponds to a particular structure. Right. So in summary, okay, we just saw a state transition process, which is achieved from the start state by applying a sequence of transition actions until we reach a terminal state. So in this process, the start state corresponds to the empty output, and the terminal state corresponds to a full output. Okay. Any intermediate state represents partially constructed outputs. Okay. So the goal of transition-based modeling is to model this dynamic process so that given a state, we know what kind of decision to choose or what kind of action to choose. This is like a decision process, DP. Okay. To illustrate, let's look at two examples. The first one is sequence segmentation. What is the state? As you can see in this figure, the state can consist of three components, where sigma represents the words, okay, or the segments that we have constructed. Omega corresponds to the current word or segment being processed. And beta corresponds to a buffer of the unhandled inputs. Okay. Now let's take Chinese word segmentation as an example. So the input sentence consists of 7 Chinese characters. All right. And our goal is to incrementally process these characters and build a word sequence in sigma. All right. The initial states have all the input in your beta. And then we gradually apply state transition actions. What can the actions be? If you remember in chapter 9, we discussed. So we can regard word segmentation as a decision process on characters, right? Where each character can either be separated as the beginning of a new word or appended to a previous word. So we can take two actions, separate or append. In this case, the first character must be separated. So let's apply segment or separate. We shift this character to omega, the temporary buffer for a current word being processed. Okay? And then we handle the next character. Somehow we need to look at the current state. All right. The first character is the Chinese character yi, and the remaining characters are 前天下雨为例, 6 characters. And according to the rest of the characters, we realize, oh, the first character is a single character word, okay? Which means take. Take the rain the day before yesterday, for example. This is the meaning of the whole sentence. So take is a word. So the next action should still be separate, all right? So after we apply separate, we put the finished word yi into the buffer sigma. And then the current character, which is the second character, into the buffer omega. So this is an unfinished word. So next character will be appended to the current character, okay, to form a word 前天, which means the day before yesterday. So the next action is append. Now beta only consists of 4 characters, 下语为例. The next is separate. We move 前天 to sigma, and we move the 4th character into buffer omega. Right? So similarly, the next action will be append, because the 5th character and the 4th character, they form 下语, which means rain. Right? And then the next action is separate. We shift the 6th character onto the buffer. And then the next action is again separate, because the 6th character Wei is 4, and the 7th character Li is example. Right? So after we shifted everything, we handled everything, we can apply a unique action called finish, right, to put the final character also onto sigma and finish. So the final state has this structure. Every word is in the sigma buffer. And the omega and the beta buffers are empty, so our whole sequence is finished. In this process, we don't directly score the segment sequence, but instead, we try to score the next action according to the current state. All right? So this is the paradigm shift. We model the process rather than the structure. What's the advantage? Let's take a look at another example, dependency parsing. We didn't look at graph-based dependency parsers before. But let's just recap. In chapter 1, we discussed this task, right? The input is a sentence, and the goal is to predict the word-word relations. So in this example, he gave her a tomato. So he is the subject of gave, and her, as well as tomato, are the objects of gave. And is a determiner that modifies tomato. As you can see, this syntactic structure is different from constituent structures. It models syntactic relations rather than syntactic spans, right? It's a different perspective of syntax. And word-word relations, they form a tree. In a sentence, there's only one word, which is the root word, which doesn't depend on another word. All the other words, they depend on exactly one word. And you can see this is a fully connected graph with n-1 arcs. And as you know by the definition, this is a tree structure. Right. So dependency parsing also predicts a tree, but rather than constituent tree, this is a dependency tree. So how do we make use of transition-based process to solve dependency parsing? Again, we define a state, okay, to store partially processed outputs, and action for incremental output building. All right. For dependency parsing, our state consists of 2 components. One is called the stack, which holds unfinished structures, and a buffer, which contains the next incoming words. Okay. Now suppose that the input is he does it here. As the start state, we put every word onto the buffer, and we have an empty stack. And then we define a sequence of actions, which I do not detail right now, but I'll specify later. The first action shifts the first word onto the stack. So he is on the stack. The next action is called left arc, which pops the top of stack and add it as a dependent of the front of the buffer. And in this case, we make he a subject of does. Here we don't specify the dependency arc label, but we just say he depends on give. The next action shifts does onto the stack. The next action is called write arc, which shifts it onto the stack and make it an object of does. The next action is reduce, which pops the top of stack, and it is now removed from the stack. The next action is again write arc, which makes here a write modifier of does, and then pushes onto the stack. The next action is reduce again, which pops the top of stack. Now here is off the stack. By now, the whole dependency tree is constructed. When we apply a finish action to terminate the parsing process. All right, so this is the shift reduce process for dependency parsing. Again, our goal is to predict the next transition action given a current state. How do we model this? All right. Here, let's consider two modeling techniques. The first is called greedy local modeling. Greedy local modeling. So the basic idea is to set the probability of an action given a current state as the modeling target. Okay. I formulate it as the equation in the middle. Now, given a state in step I-1, which is denoted as Si-1, we try to score the next action AI. Okay, so this state can be the stack and buffer for dependency parsing, right? And the AI can be either shift or left arc or right arc or reduce, whatever we choose. Intuitively, you can find that when we choose different actions, we result on different structures, right? So for example, if you don't use left arc to make he a dependent of does, you could reversely use right arc to make does depend on he, which results on a different structure. So the structural ambiguity is mapped into the action ambiguity in the state transition process. How do we score the next action given a state? Of course, we can find different ways to parameterize the model. But here in this chapter, let's consider a simple discriminative model. Because the parameterization technique is simple. We just extract features, okay, from state and action pair to model this state and action. And our model parameter is a vector which has the same size as the feature vector. In this way, our parameterization is to use a linear dot product between the model parameter vector and the feature vector to score an action given a state. All right. So, our model can be illustrated in this way. So we are given a current state, and our model tries to score all possible actions on this state, okay? And then resolve ambiguity by choosing the high scored state. So this is modeling target. So when we are given a gold standard set of data. Okay, next slide. D is equal to X and Y pairs, okay, for I equal to 1 to capital N. We're given capital N training examples, where this X is an input and Y is a gold standard output structure. We need to break this output structure into a sequence of gold actions. And these gold actions can be represented by state action pairs, right? As you saw earlier, we broke segment sequences and dependency trees into state action sequences from a start state until an end state. So this is a sequence of actions, but each action can be represented as a current state and a next decision. So given any structure, we could translate this structure into such an action sequence. And now we have the training data. If every structure is broken into a sequence action, then we can model each action individually. And we got a larger set of training examples, where each example is a current state and the next action. This is a classification problem, right? This is now a classification problem because your possible actions are finite. Separate or append, right? This is one set of action for segmentation, or shift, left arc, right arc, etc. for parsing. These actions are finite. So given any state, the state is a complex structure. We perform a classification problem to choose an action for resolving structural ambiguity. Okay, we parameterize the model, and now we know how to train this model. How do we do testing? Suppose that we have a set of gold training examples, and we train a classifier on these examples, right? So the classifier can be perceptron, SVM, log linear model, whatsoever. We have learned so many discriminative models, right? Which parameterize by theta.phi. So these linear models are generalized perceptron, right? So SVM, log linear model, and perceptron, they can be regarded as different instances of a generalized single layer neural network, which have different training objectives, right? They can all be optimized by SGD. So I will ignore how to train the model, because you all know how to train a model given a set of data. But now, given the model and given an input sentence, how do we perform word segmentation or dependency parsing? So the basic idea is we begin with a start state, okay? And the state is defined for different problems differently. And then given this state, we apply our model, okay? You can have A1, A2, ... AM resulting in a lot of different states. From these states, you select the highest scored one. Suppose that it's A1, okay? We select this state, and we advance the current state to this state. And then what do? We run the classification model again, right? Resulting in a lot of different states. And we select another state. For example, maybe we selected this state. And from this state, we apply the classification task again. We select this state until we reach a terminal state. And then we can read out the output structure from the terminal state. So this is a decision process, right? Every step we have ambiguities, but we resolve these ambiguities. That's the model. Okay. The model is a simple classifier as illustrated here. For training, you break training structures into action sequences to train it. For testing, you start from a start state and you run this process. Let's recap. A greedy local method, our model. Suppose that we're doing dependency parsing, and we train the parser as I illustrated to you earlier, and now we use the parser to do decoding or testing. The process can be like this. Initial state, sigma is empty, beta has the full sentence. First action, we do classification. And suppose that we did shift, right? And we got a new state. Key is on the stack. The state here are on the buffer. And now we need to differentiate between different actions. We might do left arc. Now he will depend on does. We might do right arc. Does will depend on he, right? We might not do shift. Or we might do shift. So which means he and does has nothing to do with each other. We could do shift again. But we could not do reduce, because if you reduce it, he will be an isolated node. The resulting structure is not a tree. So let's say from the three actions, left arc, right arc, and shift, the model assigns the highest score to left arc. So the next state will be like this. He depends on does. Again, we have to resolve ambiguities, right? So now the only action we can take is to shift, okay? Shift does onto the stack. But the next action has a lot of ambiguities. We could make does depend on it. If we do this, we do left arc. We could make it depend on does, right? If we do this, we do right arc. We could say, maybe both does and it depends on here. So if we do this, we do shift. Now let's suppose that we chose the correct action again. We did right arc. And then let's just flip through the end of the state, okay? We process it, and we process here, and we do reduce until we reach the final state, and we apply finish, okay? So this is like choosing a path from the figure I drew on the whiteboard. And I can do another animation, okay, from the next slide. So in the beginning, we have start state, and we apply actions. After actions, we advance the state, and we advance the state until we reach the final state, right? So this is a path. This is a path. State transition path, just like what we draw. Okay. But, okay. This model has a potential problem, which is every step is greedy, right? Every step is greedily taken. And our model is a local model for each action. Classification. However, if you look at the structure, right? If you look at the output structure, at every step, we might have a lot of choices. So suppose that at every step, I can take m actions, okay? And there are n steps. So the total number of possible terminal states are m to the power of n, right? So it's exponential. That is not surprising because given an input, the possible output structures are exponential. So each sequence of action will correspond to one unique structure. By mapping the structural ambiguities to decision sequence ambiguities, we don't reduce the ambiguities. So if we model everything locally, we can result in a problem, which is the local decision can be incorrect. If we're incorrect at any step, then the subsequent steps will suffer from error propagation. Because if we suppose that we made gave depend on he, right? Then the remaining structures cannot recover this error. So this is called error propagation. And our greedy local process can suffer from something similar to the label bias problem as well. Okay, if search error, the error I just mentioned to you, is a problem in decoding, right? We fail to find the highest scored sequence of actions. Then the label bias is a problem in training. We discussed the label bias in week 8, so I will not repeat it. But suppose one state, right, favors an action very much. Then the greedy model will favor a sequence of actions that have the state, right? Because the action sequence will have a high score. This is called label bias. So by building a greedy local model, we suffer from both modeling errors and decoding errors, which we don't like. How do we solve the problem? You might say, let's think about a global model with dynamic programming, just as we did for graph-based methods. What is a global model? The global model scores a whole sequence of actions as a unit, right? So that it can differentiate between good sequences and bad sequences as a whole. This is a global model. What about dynamic program? So dynamic program helps you to find the optimal sequence of actions as a whole. Can you do that? For modeling, we can do it. We can build a global model, just as we did that for sequence labeling and sequence segmentation. But for decoding, we cannot use dynamic program. Why is that so? Can you guess? It's because the last action will highly depend on the first action to take, okay? So there's no optimal sub-problem here. The whole sequence of action depends on each other. So I don't have any guarantee that my highest scored sequence of actions will contain a highest scored subsequence. There's no feature locality here. I leave this for you to imagine, to think about, to scrutinize offline. But my first action will decide the features you have in the last action. You can intuitively imagine the first action will change your state, right? Your stack will change. And your action will depend on the stack. There's no way for extracting out any independence intuitively. Of course, for specific problems, if you constrain your search space, you can extract a bit of independence. And this is what researchers did for transition-based systems. But in the end, a more elegant solution is to ignore those independencies and just assume that the whole sequence of actions is a decision process with no Markov characteristics. Okay. So if dynamic programming is infeasible, how do we train the model? And how do we do the search? So this is something you would have encountered in chapter 9 if you read the textbook. One method, okay, is to build a global model with beam search. So the global model takes the total score of every action in the sequence as the action sequence score, okay? The model is optimized globally by differentiating whole sequences of actions rather than individual actions. This is like CRF and structured perceptron, okay? I train the model using sequences of actions as a whole. For decoding, I use beam search rather than greedy search. So let's first take a look at the beam search process. I have an agenda to store k highest scored states, okay, or sequences of actions. One state represents a sequence of action. So initially, the agenda will have only the start state. And then we apply different actions. For the first action, we can only apply shift. So the next agenda contains only one state, okay? However, the next action has 3 different choices, as I mentioned earlier, right? You could either shift or left arc, etc. So it will result on 3 different states. Now suppose that the size of the beam is 3. So the next step, the agenda can contain all 3 new states. Next step, from the 3 states, we could each apply different actions. So it will result on a lot of new states. But let's suppose that we only store the highest scored 3 in the agenda. We prune the rest. We prune the lower scored state away, right? And next step, we do similar things. From the 3 remaining in the agenda, we apply different actions to each. And then we result in new states. Now suppose that we put the gold state or the highest scored state in blue. I circled it. Next step, the gold state might be in the second location, okay? So in this step, if we do greedy local search, we will lose it, the globally highest scored state. We will lose it. But in beam search, if your beam size is large enough, in the next step, it can be recovered to the top of the agenda again. And then you just repeat and repeat until you reach a final agenda, which contains all different terminal states. Imagine that the high scored sequence of actions are now on top of the agenda, and you could take it out. So this is search, beam search. And now you say, wait a moment. So beam search is not exact inference. For beam search, you can reduce error propagation from greedy local search, right? But you cannot guarantee that the highest scored action sequence will not be pruned in the process. How do you solve the problem? We could apply training to help you reduce search errors. The basic idea I will illustrate to you here. Let's first look at the modeling. Okay. As I mentioned earlier, I want to model the whole sequence of actions as a unit. As a result, our discriminative model, okay, parameterized by theta dot phi, will look something like this. Score of a sequence of action capital A given an input x is equal to theta dot phi capital A and x. So we extract features from the action sequence or state transition process. We result in a global feature vector for the sequence. And then we use a model parameter theta dot this feature vector to score the sequence of actions. Now this doesn't support beam search, as I mentioned to you earlier, right? Because even with beam search, you need a local decision. So we take a similar trick as CRF. We factorize the global feature vector into local feature vectors. In other words, we still extract features from each local decision. So the global feature vector phi is equal to the sum of local feature vectors from each step. Phi small a and x. This small a is the local decision as our local model. As a result, in the last equation, we could do a mapping, right? We could apply commutativity of addition. No, actually, this is summation and multiplication, distributivity. So theta dot, the sum of local phi, is equal to the sum of theta dot local phi, right? So again, now if you look at theta dot local phi, this is like a local action score now. Very similar to what we did for CRF. We factorize the feature so that you have a energy or a local score on each factorized click. So this is how you do the global model. Okay. While I haven't mentioned how to train this global model, let's combine this global model with beam search first. This is the pseudocode, okay? We just formulate the beam search process I just mentioned to you earlier. From the start state, we repeatedly apply all possible actions to the current items in the agenda. From the new items, we take k highest scored one and we put back to the agenda. We repeat this until all the items in the agenda are final states. Let's recap. So initially, the agenda contains only he does it here, the beginning state. And then we apply shift to result in a new agenda. Then we apply 3 different actions to result in a new agenda. Then for each item in the agenda, we apply new actions and we leave the highest scored ones in the agenda. And we repeat this. Now suppose that the globally optimal sequence is in blue and we apply new actions. Now the new globally optimal sequence is in a second location. And we repeatedly apply new actions. It is recovered to the first item, and then we continue until we stop, okay? So this is the beam search process, where in each step, we just apply the theta dot local phi, okay? But our goal is to recover the blue state, which is the globally optimal sum of theta dot local phi, okay? We need to train the model now. Now imagine that we use the global perceptron or a global SVM, we train this model. we apply this model to beam search. We could suffer from search errors, right? If the gold or the high scored item is pruned in the middle. How do we address the problem? Our main idea is we could design a learning algorithm to guide the search process. Okay, the training goal is no longer to differentiate correct action sequence and incorrect action sequence in the absolute sense, but to guide the beam search process step by step so that we try to reduce search errors. I illustrate this in the figure here, where the red thing shows the gold standard action sequence. Okay, the black box shows the agenda, the beam, okay? So from the start state, we could advance the state, and at every step, we hold the high scored action sequence in the beam. Now imagine, as the decoding process goes through, at one step, the gold sequence falls off the agenda. Now we made a search error, right? So we want to correct this search error. How do we do it? If we know the gold sequence here, we could take this action sequence as a positive example. And the highest scored action sequence, which is the top of agenda, as a negative example. We could do a perceptron training step, right? By adjusting the model so that we add the feature of the gold example, positive example, to the model parameter. And we subtract the feature of the negative example from the model parameter. If we do that, as we learn from week 3, next time we do the same search process, the gold action sequence will be more likely scored higher than the negative one, okay? So we reduce search error. Inspired by this observation, we can define a training algorithm, as I state, okay, here. When we're given a set of training data, we transform each training structure into a gold action sequence. Then we train a model by using a perceptron-like algorithm, which is integrated into the beam search process. Okay, if you remember the old perceptron training process, we use dynamic programming to find the negative example, right? The negative example is the highest scored example if it is not correct. But now we use beam search to find a negative example. Okay, we run beam search and we observe the gold sequence. If it falls off the beam, we stop the search process. And we take this one as a positive example, and I take the highest scored action sequence as a negative example. I perform perceptron update, okay? The only change as compared with the perceptron algorithm we learned in week 3 is that we use beam search to find a negative example rather than dynamic program, because now we cannot apply dynamic program. Right. So pseudocode is shown in the next slide. You can read the details offline, but basically what we did is what I described before. We can go through the set of training examples for multiple iterations. And for each training example, we monitor the beam search process until it makes an error. When it makes an error, we cut the search process. We don't continue the search process because the next steps will be irrelevant. They will be comparing incorrect examples with incorrect examples. I want the gold example, okay? So until the search error happens, we find a negative example. We take the gold example and we perform a perceptron update. What if the search process goes until the end? If the search process goes until the end, then our final agenda must contain a gold item, right? Gold action sequence. Now, the criteria is if the gold action sequence is not ranked on top of the agenda, we still need to update the model. So we take the top of the agenda as a negative example, and we perform the perceptron. To differentiate the middle error and the final error, we call the perceptron update in the middle of the beam search early update. And we call the perceptron update if your search finishes without losing the gold sequence, the final update, okay? So in this perceptron algorithm, you have two update methods. One is called early update, one is called final update, depending on whether your beam search makes an error in the middle, okay? A little bit more complicated than the beam search algorithm in week 4, because for that algorithm, we only have the final update. There's no search error to fix. But for beam search, we have early update and final update, two models. The pseudocode here basically contains both sorts of updates. I leave it to you to read offline. Okay. Now, equipped with the global model, okay, parameterized by theta.phi, okay, trained using perceptron-guided beam search, and decoding using beam search, we can roll up our sleeves and build a transition-based model for every structure prediction problem. And our job is easy because we don't have to define a special dynamic program for every structure as we went through weeks 7, 8, 9, and 10, right? We saw sequences, segments, and trees. Each of them have different dynamic programs. But for transition-based structure prediction, all that we need to deal with is a transition process. So the model framework is the same for every structure. That's the advantage. So what do we need to define? We need to do two things to apply our transition-based framework to a specific structure. First, we need to translate the structure into a state transition process, a decision process. We saw that for segmentation and dependency parsing. Second, we need to parameterize the model by defining a set of features to represent the state action pair, right? We only need to do these two things. And after these are done, we plug in the state transition process and features into the model framework here. We can solve any structure prediction problems. And as I go through these examples, I illustrate the advantage of transition-based methods as compared with graph-based methods. First, let's look at constituent parsing. Okay? As I mentioned to you earlier, the two steps in building a transition-based model is first to define the state transition process, and second, to define the features. Okay, first, how do we translate a constituent tree building process into a state transition decision process? Our memory is still fresh. In week 10, we learned this CKY parser, PCFG. In order to build such a parser, we could define a transition process like this. We need to define a state and a set of actions. The state consists of a stack and a buffer, just as for dependency parsing. And the actions will incrementally take words off the buffer and build structures on the stack. So let's look at the actions one by one. So the first one, okay, suppose you have a sequence of words, each assign a part of speech on the buffer. You want to build a tree, okay? The first one is shift. You move the first word from the buffer onto the stack. Next action could be shift. Next action again is shift. Now 3 words are on the stack. Next action is reduce R and P. So basically this is a binary action. You took little boy, 2 words, off the stack and build a noun phrase NP node covering little boy. R means the head word is on the right, boy is the head word. And then you make another binary reduce action. You take the top 2 nodes off the stack and you build a new noun phrase node. Now the little boy is a noun phrase. Next you do shift. Like on the stack. And then you do another 2 shifts. Red and tomatoes are on the stack. And then you do another reduce right noun phrase. You take the top 2 nodes, red tomatoes, off the stack, and you build a noun phrase covering the 2 words. And then you do a binary reduce left verb phrase. You take the top 2 nodes, likes and red tomatoes, off the stack, and you make it a verb phrase where the head is on the left. Then you shift period onto the stack. And then you do another reduce left. You make a sentence temporary node. So likes, red tomatoes, and period is now combined. And then you do another right reduce. The little boy likes red tomatoes is now a sentence node. Now with this, you form a full binarized tree on the stack. And you can apply a finish action to finish parsing. Okay? So far, we finished the first step. We made constituent parsing a state transition process. As you can notice, so this framework builds binary trees, right? In Chomsky normal form. Just like CKY, it doesn't build arbitrary branching trees. The next step is to define features for the problem. Okay, how do we define features? The current slide shows you a state which contains the stack sigma and a buffer beta. What we want to do is we want to extract a lot of patterns from the current state so that we can decide what next action to take. Now, these patterns are very important since it helps us to resolve ambiguities in structures. When you see this current state, okay, where the is on the stack, little boy is on the stack, and likes red tomatoes are on the buffer, what kind of patterns do you think are useful in disambiguating the next action? I think both patterns on the stack and on the buffer will help, right? If you know somehow the stack contains the determiner and a noun phrase, and the next things in the buffer is a verb, you probably know, I probably want to combine the determiner with the noun phrase first to make a full noun phrase before I shift the verb onto the stack, so that I will not lose a chance to combine the determiner with the noun phrase, right? So this resolves the ambiguity. After you shift the verb, you can only combine the noun phrase with the verb first, and the determiner will be dangling. It will be wrong, okay? Based on this intuition, we can define the following features, as shown in the next slide. We can extract a lot of features, like the first item on the stack, the second item on the stack, etc. And the front item on the buffer, the second item on the buffer, etc. For each item, we could extract what's the word, what is the part of speech, okay, what it is the constituent label. You know, for the words on the stack, you have constituent nodes, right? For example, little boy is a noun phrase node. With this node, the head word is boy. So you can extract the head word from the node, the constituent label from the node, and the part of speech of the head word. All of these are useful for disambiguation. In addition to extract single node features, you could also combine two node features, such as the top node on the stack and the front node on the buffer. You combine them. So what if the top of the stack is the word boy, and the next word is likes on the buffer? This composition can also help you disambiguate next actions. Okay. I leave it to you to read the details of all these features. The next slide gives you an example. The example is S0P, S0C. What does it mean? It means the top of the stack. I look at the part of speech and the constituent label. If the state is shown in the figure below, then the top of stack, the part of speech, and the constituent composition will be VBZ and VP, because the head word part of speech is past tense verb, is singular third person verb, and the corresponding constituent label is a verb phrase. Similarly, S1P, S1C, okay, the part of speech and constituent label of the second word on the stack will be a noun and a noun phrase because it corresponds to a noun phrase, the little boy. All right, you can extract features by mapping the feature templates in the previous slide to the current state and action pair. Note, every feature has to be combined with every action in order to score that action. So if you just extract feature from the state, it doesn't make sense. Okay, what I want to say is, if you look at these features, they're highly non-local, right? Last week, all the models have to constrain their features within the same constituent rule. But in here, obviously, I covered already two constituent nodes with their head words. If you consider the buffer words as well, it will be highly non-local. This means transition-based systems has the advantage of defining rich non-local features, which helps you disambiguate. This is one advantage. The second advantage is, if you think about the beam search decoding process, the number of steps you take is almost linear to the number of input words, right? As a result, beam search has a very low runtime complexity compared to CKY in the last week. Linear versus n to the power of 5. As a result, such transition-based constituent parsers with global modeling beam search and rich features can strongly outperform traditional CKY parsers. So this shows you one advantage of transition-based modeling. Without further assay, let's go through dependency parsing as well. We saw a dependency parser, but we didn't formally denote it. Let's do it now. It turns out that there are different ways to translate a dependency tree into a state transition process. And here, let's look at two. One is called the arc standard parser. Okay. What is arc standard parser? Let's first define the state. It consists of a stack and a buffer. I won't repeat the introduction, but the actions consist of three types. One is shift, one is left arc X, one is right arc X. Their purpose is shown in the next slide. Shift just moves the front item from the buffer onto the stack. Left arc removes the top two items off the stack and makes the left item a dependent of the right item, okay? And then put the right item back onto the stack. Or you can imagine it as only removing the second top item off the stack and making it a dependent on the top of stack. So right arc does the reverse. Three actions. Next slide shows you a deduction system of the actions, just as I showed for constituent parsing. Now let's use the sentence "he gave her a tomato" for example to illustrate the process. So we first shift he onto the stack, and then we do a shift gave onto the stack. We do left arc subject. Note that subject is an action, right? So action space is larger, but you can assign dependency arc labels. So he is the subject of gave now. And then you do shift her, and then you do right arc I object. Okay, indirect object of her as gave. And then you shift and you shift tomato, and do left arc determiner to make depend on tomato, and then you do right arc the object. So to make tomato a direct object of gave. And then you finish the parsing process. Okay. So this is a transition scheme. And how do we define the features? So I first show you an example state where the front items on the stack are shown as S0, S1, etc. And front items on the buffer are shown as B0, B1, etc. Okay. Again, to predict the next section, you need to extract the rich features from the stack and the buffer. The next slide shows you a set of feature templates. These are information composition from sigma and beta. And you consider the words, part of speech, dependency labels, etc. I will not detail the content. I leave it for you to read. Okay, this is arc standard parser. After we get the transition scheme and features, we plug it into the model framework, and we can directly run the parser. The next is arc-eager parser. It's a different state transition scheme for the same task. Okay, how do we define the state? Again, stack and buffer. But now we have four actions in the scheme: shift, left arc, right arc, and reduce. What do they do? So the next figure illustrates this. Shift will move the front of the buffer onto the stack. Left arc will remove the top of stack and make it dependent on the front of the buffer. Right arc will shift the front of buffer onto the stack and make it dependent on the top of the stack. Reduce will remove the top of stack. Exactly as you realize, this arc-eager parser is the parser I illustrated in the beginning of the lecture. So if you run the parser again, okay, using he does it here, we just recap the previous process. We first shift he onto the stack and do left arc to make he a subject. Note here, the action contains subj, okay, the dependency arc label. Then we do shift does onto the stack, and we do a right arc object to make it the dependent of does. And then we reduce it, and then we do a right arc again to make here depend on does. And then we do reduce again, and then we finish. Okay. It turns out that arc-eager parser and arc-standard parser use different actions to achieve the same task. And by using them as an example, I show you when you design the state transition process, you have a lot of choices for different structures. The next example shows you one interesting phenomenon, which is called non-projective dependency parsing. So far, the dependency trees, they are projective in the sense that if you draw the tree in a paper, there are no crossing arcs. But non-projective trees are trees that have crossing arcs. Here is an example. A hearing was scheduled on this today, okay? So on depends on hearing. But today it depends on scheduled. These two dependency arcs, they cross each other. So it turns out that non-projective dependency trees cannot be processed by either arc-eager parser or arc-standard parser. How do we define a set of actions to handle them? So if you carefully observe the output, you find that on this modifies a hearing so that you can rephrase the sentence into something like, a hearing on this was scheduled today. If you move on this, okay, immediately after hearing, then the non-projective dependency tree will become projective, and your arc-standard parser can handle it. Given this observation, we can add a new action to the arc-standard parser called swap, which swaps the top of stack and the front of the buffer. Basically, it feeds the top of stack back into the buffer, okay? Due to time constraints, let me just use an example to illustrate this. The process is same. It's similar to arc-standard parsing, okay? We have a beginning state, and the buffer contains a hearing was scheduled on this today. We first shift and then we next shift hearing. And then we do a left arc determinant to make depend on hearing. And then we shift was. And then we shift scheduled. And then we shift. Okay. And after here, I want to swap on this, okay? Close to a hearing, right? So now we apply a swap action. So this scheduled will be put back onto the buffer. Okay. So the sentence now read something like, a hearing was on, scheduled this today. Now, we continue a swap. We move was back to the parser. So the sentence reads something like, a hearing on was scheduled this today. And next, we apply shift, shift, and shift again. we shift was scheduled this onto the stack. And now we want to swap the word this with was scheduled. What do? We apply two swap actions again. We first swap scheduled and this by putting scheduled back onto the buffer. And then we apply swap again to swap was back onto the buffer. And now the sentence finally reads something like, a hearing on this was scheduled today. So the rest of the parsing process will be standard. For example, we do right arc p object to make this depend on. And then we do another right arc and mode to make on this the modifier of hearing. And then we do shift left arc subject to make hearing a subject of was. And then we shift, and then we shift. And then we do right arc temp to make today depend on scheduled. We make left arc VG to make was depend on scheduled. And we finish. We get the correct tree. Okay. This is for dependency parsing. Now let's move on to the final topic of today, joint models. As you saw from the examples earlier, right? Transition-based systems are very flexible. They are not constrained by the dynamic programming signatures so that you are free on defining arbitrary features. Because of this, you can handle any complex structures. And here I use joint models as an example. What is a joint model? A joint model uses one model to solve a pipeline of tasks. What are they? For example, part-of-speech tagging and parsing can be a pipeline. Given a sentence, you first apply a part-of-speech on each word, and then you build a tree structure on top of it. Now, traditional models, as we discussed in the previous chapters, you have to do part-of-speech tagging before you do parsing. There's a disadvantage to that, because part-of-speech tagging errors will propagate to parsing. There's no chance for your parser to recover part-of-speech tagging errors. A second disadvantage is that parsing features cannot help you differentiate part-of-speech ambiguities. But intuitively, if you know the syntactic structure, you can better resolve part-of-speech errors. If you build a joint model, okay, you extract features from parsing and part-of-speech tagging simultaneously. And you do decoding as one task so that you reduce error propagation and you allow features from different tasks, they interact so that you have a better model. And these models are very challenging for dynamic programs because the search space is complex. The structure is subtle. I give you two examples to illustrate how straightforward a transition-based system can solve such joint tasks. First, let's consider joint part-of-speech tagging and parsing. The input is a word sequence. The output is a structure where each word contains a part-of-speech label, and you have a tree. Each arc on the tree has labels. How do you do this? It turns out that the only difference you make on top of an arc standard parser is to add a part-of-speech label to shift actions so that the original shift becomes shift X. Again, I use he won the game, the simple sentence, for example. The start state has something like this. You first do a shift VBD action. Oh no, you first do a shift PRP action. You shift he onto the stack as a pronoun. And then you shift 1 onto the stack as a past tense verb. And then you do a left arc and subject action to make he the subject of 1. And then you shift DT to make the a determiner. And then you shift NN to make game a noun. And then you do a left arc DET to make the depend on game. And then you do a right arc DObj to make game depend on 1. And then you finish parsing. It's so simple and elegant. You resolve joint task ambiguity using a simple set of actions. Next, I show you a very complex example. Joint word segmentation, part of speech tagging and parsing. The input is a sequence of characters. The output is a dependency tree, where the dependency arcs are built on words. Every word has a part of speech, and every arc has a label. This consists of segmentation ambiguity, part of speech ambiguity, and dependency arc ambiguity. To make things more complicated, I also add arcs between characters within the same word. For example, the first word, 林业局, Wood Industry Bureau, okay, or Wood Industry Office. 林 depends on 业, okay, what kind of industry? And 林业 depends on office, 局, what kind of bureau? What kind of office? Okay. Similarly, 副局长, deputy office manager. 局 depends on 长. What kind of manager? 副 depends on 局长. What kind of office manager, right? So every Chinese word, if you carefully look into it, the characters, they depend on each other. They make syntactic categories. Now, I finally result on a very complex structure where you have words, part of speech, dependency labels between words, and also dependency labels between characters. You can hardly imagine how you build a dynamic program to solve all these ambiguities. But we can translate this into a state transition process. Okay, the state consists of 3 components. Sigma, partially built dependency tree. Delta, word structures. Beta, incoming characters. And the output also consists of characters between, dependency labels between characters and dependency characters between words. The actions, next slide. Several different actions. Okay, well, it at least depends on 3 types of actions. Actions that build arcs between characters within a word, actions that finishes a word and assigns part of speech. This is like segmentation actions, and actions that build dependency arcs between words. Okay. Rather than showing you the details of every action, let's just move on directly to the animation. Okay. Suppose that the sentence is 6 characters. 我来到会议室. What do we do? Initially, everything is on beta. Sigma and delta are both empty. I first shift 我 onto the stack. Okay. And then I finish this as a single word, okay? And I assign a pronoun into it. And then next, I shift this pronoun onto the stack sigma. And then I next handle the next character 来. Okay. I first shift Lai onto sigma. And then I perform a left arc, okay, to make Lai depend on Dao. And then I finish this word. I make Lai Dao a verb. And then I shift Lai Dao. Oh no, and then I do a left arc, okay, to make 我 a subject of Lai Dao. And then I shift Lai Dao onto the stack sigma. And then I shift Hui onto the partially processed stack of characters. And then I do a right arc, Yi, okay, to make Hui Yi, meeting, a partial word. And then I do another character action to make Hui Yi depend on Shi, meeting room. And then I finish Hui Yi Shi as a single word, now, right? And then I do a word level right arc to make Hui Yi Shi depend on Lai Dao as an object. And then I reduce on the word level to remove Hui Yi Shi from the stack sigma. And then I can apply a finish action. The parsing process is done. I didn't discuss the features, but actually this whole process is an academic paper. So far, I used two examples to show you how transition-based methods can solve very complex output structures in a relatively straightforward manner. And so far, I can conclude this lecture. In this week, we learned a new paradigm for structured prediction, transition-based methods. So we serialize any structure into a decision process. And I showed you how this process can be easily modeled using a discriminative structure. Next week, we move on to the third part of the whole course, namely neural models. From next week onward, I will show you how to build neural networks as an extension to the single layer network in week 4 to solve classification and structure prediction tasks. Okay, so see you next week.